Okay, hi team, how are you doing? What I'm going to do this morning is just go through the content that we did this week, which is the work done by a gas. I'm going to be recording the screen. As you can see, it's set up onto the web page that we've got for this. Just going to go through the key content, what you really need to be comfortable with, and just make sure that you're able to then do the quiz at the bottom of the page. So first things first, what we need to do is be comfortable with the idea that there is a formula that you need to know, and this formula is just here. We talked through the idea that essentially work can be calculated if we know force and displacement. Now, what we did this week is we introduced the idea that a gas can do that work, and that gas can be measured in two key ways, and that is firstly through gas pressure, which is P, and volume, which is V. We've come across these before on our formula sheets, and if we know the pressure and the volume of a gas, we can calculate the work that gas is able to do. Where this kind of starts off is with the idea around a piston, and we relate this to James Watt, who was the kind of father of the internal combustion engine, and he developed this kind of piston idea whereby gas could do work, and gas does work essentially by being expanded or contracted, and we do that by heating and cooling the gas. So what we should be comfortable with, two really key concepts here. Firstly is that heated gases expand, and cooled gases contract. By expanding and contracting, either we can do work onto the gas, or the gas can do the work for us. And we can see in this animation up here on the right hand side that the gas is doing work there to move a piston, and that can be connected up to a gear set, and then that can be connected to some wheels. Now we call this pressure volume work, or PV work, and we demonstrated this in the lab doing a practical, which I'll talk about in a minute. Now, when a gas is heated by an external source, now I demonstrated to you guys a simple heat engine that sat on top of a cup of hot water. That was our heat source. It's an external heat source. Energy is added into a system, and a system essentially that contains gas molecules. Now, as the heat goes in, the gas molecules begin to move more. They get kinetic energy. They gain that kinetic energy. The increase in kinetic energy is essentially observed in an increase in temperature. Now, what we need to be comfortable with in our piston, we don't want temperature to increase. If temperature increases, that gas could explode, and that piston could explode. So the piston's designed so that as the temperature increases, the pressure will increase, and what that causes is that piston to essentially increase in volume. In turn, what that does is it drops the volume, and we'll come to this in a minute. So as the temperature of the gas increases, the gas molecules move faster and collide more, and essentially this transfers energy into the piston. So the gas is doing work. This is given by this formula. Again, we're given this formula in the exam, but we do need to be comfortable with what the letters mean. So W is work by gas, measured in joules. It's an energy transfer. And we know this if we take pressure and we multiply it by the change in volume. So pressure measured in pascals or kilopascals, and change in volume measured in litres. Okay, so that is a really important formula to be comfortable using that, and the quiz at the bottom will make sure that you can work through that. We then did a practical, so if any of you missed the session, essentially what we did is we set up, just quickly move this down a little bit, we set up a syringe which was sealed. So there's a syringe there, and a crocodile clip sealed the syringe into a sealed vessel essentially. So inside it was a set amount of air. No air could leave or enter that vessel. And what we did is we attached masses to the syringe, and in doing so, that pulled down on the plunger. And what that did is it increased the volume inside the syringe, and in turn, it changed the pressure. Now, what we can compare this to is a spring. What we essentially did is we stretched the air. So as the air was stretched in that syringe, it was stretched, and then if you let go, what happened is the air recoiled and pulled the plunger back up. And that is essentially that recoil is the gas doing work. And what we can do is if we can calculate the work done by the gas at a given volume and pressure. Our data set for the practical is contained within this document. So you can open that up by clicking the full screen button. You can edit that data by making a copy of it. You feel free to do so. The key thing there is that you should have pressure and volume change data that you can then work on. We didn't do any graph plotting. I didn't see any value in it. But what we found was that there was a relationship between pressure and volume. And what we found is that as we increase the volume of the syringe, the pressure decreased. And we can see that in the trend line, essentially here. So there's a trend line, and we found that the data that we collected, ignore the fact that's not a straight line, it's not the end of the world, but we understand then that essentially Boyles Law states that pressure is inversely proportionate to the volume, and our data agreed with Boyles Law, like so. So that's good news. Excellent. Let's just get rid of those lines. Okay, so to explain Boyles Law, we can use these diagrams here. So these diagrams essentially show, firstly, the piston at high pressure. So that's where the piston is pushed close to the end. The gas is at high pressure. It's in a low volume. And what happens in our example is that the plunger is moved back. So that's in the bottom image. As the volume increases, the pressure drops. And we can see this inversely proportionate relationship in the data that we collected. So we should be able to understand what's going on here. Just relate it essentially to the number of molecules in that piston remaining the same and the temperature remaining the same. So that's really important when we think about Boyles Law, is that those two things stay the same. The only things changing is the pressure and the volume. So again, if we go back to that graph is the data that we collected. It agrees with Boyles Law, and it explains to us the relationship between pressure and volume. And these are going to be really important concepts as we move through the unit, and we start to explain how heat engines essentially work. Now, this bit here is something that you can do. So it's called the hard bit. It's not that hard. What you need to do is you need to take your volume data and you need to go 1 divided by the volume, and that's the change in volume. What this does is it allows us to produce what should be a straight line graph, a linear positive correlation. Now, this particular graph that we have here on the right hand side is, again, it's based on a data set that we collected. What we can see is that this isn't a straight line. We have a slight curved line, and this demonstrates that our equipment wasn't really designed for doing this particular type of practical. The plastic syringe distorts when it's clamped, and that introduces friction. So what we can actually say is that this particular energy transfer system isn't particularly efficient. There's energy losses. And that's good, because what we're going to do next week is we'll start to talk about efficiency and what that actually means. Now, the key thing to note is if we did this in perfect conditions and we used a syringe that didn't warp, we should get a straight line. And what we would actually find is if we change the pressure and the 1 over volume changes proportionately. And what we actually find then is that pressure and volume are constant. So this here is going to be useful to us later on. So essentially what this means, you see that there at the bottom, the pressure of a gas in a constant volume can only change if the amount of gas in this system changes, or if the energy is input into the system. And that makes sense hopefully to us. So if you have a piston which is sealed, the only way you can make the pressure of that gas change is either by introducing more gas into it, so pumping air into that piston and making that volume change, or by putting energy in, so you input heat. So how does this relate to work done? Okay, so at this point, we're going to recap essentially what we understand is that gas inside a piston can do one of two things. Firstly, it can expand. So the gas expands, and this is shown in this diagram here on the right hand side. And we can see that the volume increases, and as the volume increases, the pressure decreases. The pressure is related to how close those particles are together. If you increase the volume, those particles are less close, and there's less collisions between them, and that's relating to kinetic theory. What that does is reduces the pressure. Now, on the other hand, if we compress the gas, so push down on that plunger, what that does is it pushes those molecules closer together. Essentially, that increases the number of collisions between those particles, and that increases the pressure. So when a piston does either of these things, energy is required. So either we're having to push down on the plunger or we're having to pull up on it. Either way, the gas will act like a spring. So either you can have a spring that you squash, which then recoils back to its original shape, or you can have a spring which you stretch, and then that recoils back to what it is. So different pistons will work in different ways. But what we need to understand in this case is in either way, we're having to do some input of energy. So either the work is done on the gas or it's done by the gas. Now, if the work is done on the gas, as we can see here, I've just drawn right through it. Let's get rid of that. If the work is done on the gas, it is classed as negative work done. What that means is essentially the gas is not doing the work. Some kind of external source. So it could be heat going in. It's confusing because that's how is that negative work done? Well, essentially what you're doing is you're storing energy into the gas. So the gas is taking on that energy, and then what happens at the next stage is the work done is by the gas, and at this point it's positive. So that is the gas essentially using up the stored energy inside it. And again, if you just think about the idea of gas being like a spring, so either you're squashing it or you're stretching it, and then it's recoiling back to its original shape. And that's how the energy transfer happens. And what we're going to do in the next couple of weeks is we're going to start to look at graphs like this. So don't worry too much about this graph just yet, but what it does show is pressure against volume, and it shows us a cycle. So what we can see here essentially is 1, 2, 3, and 4. 4 different stages of a cycle in an engine, essentially, and this is what we're going to use to explain how an engine works. We don't need to do that at this stage. Okay, we can essentially we can qualify this work done using the formula. So we did that with the data. You knew the pressure at a given mass added to the syringe, and you knew the change in volume. You multiplied the two, and that told you the work done by that gas when the weight is removed. Basically, what this bit talks you through is that you can actually use the formula to calculate work done, but you can also use a graph, which is shown here. If you were to plot pressure against volume, the area under the line is the work done. Now, you're not going to be expected to calculate the area under a curve. As you can see, the distance between A and B there is curved. We're not going to expect you to be able to do that, and that's why we use the formula above. Okay, so that's essentially what you're calculating. Further reading, again, there's some really helpful websites here that you need to have a look at, see if you can get your head around this in a bit more depth. You get your head around this bit, it will really help your understanding of the next couple of topics. We then talked about this bit. So what we know is that work done is equal to force times displacement, which is our first formula from last week. We also know that work done is pressure times the change in volume. So from this, we can actually say that force times displacement is equal to pressure times change in volume. So you can use, they're essentially equal to each other. Okay. Calculate work done using both formulas on the data collected in the method above, and the two results will be almost identical. What this actually means is we didn't actually need to calculate the pressure and the volume. We could actually have measured the force down on the syringe and the distance that syringe moved each time, and it would have given us the same results. But it's important that we understand where this comes from. What you need to do now, once you've read through all of this, you've made notes, you're happy with the content, have a go at this recap test here. Make sure you submit that, and that'll be it. If you've got any issues at all, drop me an email, and we're all good. Okay, so all the best. Have a good day.